Hi everyone. Today I'm going to talk to you about KV caching or key value caching. It is one of the ways that we can save compute when we are using ChatGPT models. In order to explain what KV caching is, we're going to sort of step through the various aspects of the ChatGPT model and understand each of those sort of simple explanations of each of these aspects and then understand KV caching. The first important thing that we are going to understand is how does autoregressive computation work. And for each of these concepts, I'm going to show you an online resource which gives a nice sort of illustration of how the concept works. So let's start with autoregression. So we give a prompt to ChatGPT. Let's say the prompt is recite the text, the first law, and then there is this token which says, the end of sentence. The ChatGPT first predicts a word which is A, and then it adds A to the prompt, which is what happens here, and then it predicts the word robot, which it adds to the prompt. The next word is may, which it predicts, and it adds that to the prompt. So at each step, ChatGPT predicts a word and it adds that word to the prompt, and then it predicts the next word, and it keeps on going like that. We made a previous video about how to do inference in ChatGPT from scratch. If you go and look at this video, and this is the notebook that the video refers to, you can see the exact same thing. We gave the prompt once upon a time there was a land, and then we were able to sort of produce this output text once upon a time there was a land of the dead, and the dead were the living, and so on. In that video, we sort of tried to demonstrate the autoregressive nature of ChatGPT, where the first step, you can see this is the input prompt, and it predicted this token 286, which probably corresponds to off. Okay, and then in the next sort of step, it tagged on that 286 to the original prompt, and then output the token 262, and then in the third step, it tagged the 262 token, appended it to the original prompt, and so on and so forth. So that explains the idea of autoregression. Now, let's explain what happens in each of these autoregression steps. And by now, you know this very well. What happens is this idea of attention. And again, I always come back to the illustrated transformer by LLMs, which explains attention the best. So let's see what that does. In the attention layer, for each of these tokens, we get an embedding. And then it runs to this self-attention block, and it produces another embedding, which is simply the weighted value of each of these embeddings. So there is a weight. So first we produce a value vector from this embedding, and then we weight the value vector of each of these embeddings and produce a weighted average of these value vectors, and that is what the Z represents, right? And then if you go through this whole sort of, so here you can see that we take these embeddings and produce the query key and the value vectors. And then we basically find the weights by multiplying the query and the key vectors, and then use those weights to average the value vectors. The final thing that you need to understand is the idea of causal masking, which means that this is a great example from Sebastian Rachka's book, which again I will put a link below. But the idea here is these are the multiplications of the Q and the K vectors. And that produces these weights here, right? But we do not want to attend to future weights. So for the word your, we cannot attend to future weights like journey. So if the word is your journey starts with one step, we can only attend to your, and that has the weight of 1. And now with journey, we can only attend to journey and your, which is the previous word and the word itself. And you can see we have sort of two different weights which add up to 1. And then for the starts, we have sort of 3 different weights which add up to 1. And so the embedding is the weighted average of the values with value vectors with these weights. So that's the idea of causal sort of masking. So now let's understand what happens during KV caching. So the important question we want to ask is, if we want to reduce the computation, is there some redundant computation that is happening that we can sort of simply take out? So remember, so all of these steps, all of these sort of query key value embedding calculations keep on happening at step 1, step 2, step 3, and so on, right? Are some of these calculations redundant? That is the main question that KV caching is asking. And there is. Why? Because if you look carefully at these tokens here, let's say that we start with your journey starts with 1 and ask it to produce the next word, and it produces the word step. Okay, so when it produces the word step, at that time it already calculates, this whole matrix except the last row, right? So everything except the last row is calculated. Now we tag on step, similar to how we tag on 262, we tag on the token for step, and then we again come back to the same matrix, only we have the last sort of row and the last column which we added, which means that we are again calculating the exact same embedding, the exact same query key, and the exact same dot products, which are sort of everything except the last row and the last column, right? So that is a redundant calculation. And what KV caching is saying is that why don't we cache these key and the value vectors so that we can simply look it up in a table instead of doing this expensive matrix operation again. Let's look at this blog from Neptune.ai, and again I will link to this blog. This is, I think, the best what I would say the best visual explanation of KV caching. And now that you understand the whole concept, let's see how this visual explanation makes sense. So in this example, this is an even simpler example where we start with a 1 token prompt. So instead of giving these bunch of tokens as a prompt, let's say we give 1 single token once. And let's say, and what would happen in that case? We would just calculate the query and the key and Q1 multiplied by K1. This is simply, in this example, this is simply this value of 1, right? So that is the only thing we will calculate in the first step. The next autoregressive step, we will come back with another token, which is maybe once we will calculate upon, okay? And then we take the query of the query from the next predicted token, and then we calculate, and then we multiply it with the K1 and K2 to get the second row, which is Q2 K1 and Q2 K2. But remember, in the second step, we are again calculating Q1 K1. The new calculation is simply the second row, okay? And this is what they say. K1 was computed needlessly. We already calculated this before. And this is the same exact element as the previous forward pass. So this is the basic idea of KV caching, is that we simply look up Q1, K1 instead of making this expensive matrix multiplication again. Okay, and the thing that makes sort of these GPT models very expensive is that sort of grows quadratically with time, and then that's the expensive part of it, which makes it compute expensive. So now, in the third step, we've already calculated the first and the second row. We simply need to look it up, and we simply need to make these 3 calculations in the last row and not worry about the first 2 rows. And that is what KV caching does. And then you can code it up like they show you here. You can sort of do KV caching very easily in PyTorch, and you can look at how the runtime sort of reduces to 1/3 without sort of KV caching versus with KV caching. And so that is the basic idea of KV caching, and I didn't want to write any code here, but wanted to give you a basic idea of what's happening in KV caching. And if you want to remember it simply, basically you are taking, to produce your sort of output, ChatGPT is taking multiple steps. And in each of these steps, to produce this whole output, ChatGPT took so many of these steps, and in each of these steps, it produces one single word. But when it produces that single word, it keeps on computing query key values from all these previous tokens. But it has already computed many of these values except the last one in the previous steps. And so we can simply sort of keep it in a hash table and look it up. And that is what the KV caching does. I hope I was able to explain to you the concept of KV caching. But if you have any questions, feel free to comment, and I will do my best to give you a better explanation. Thank you.